So, first of all, there's a few different gas law relationships. The first is called Boyle's law, which says that pressure and volume are directly related. So, if you were to decrease the volume of a container and therefore reduce its surface area, the pressure would go up. And if you remember that pressure is force per unit area, that should make sense, assuming your temperature is constant. There's Charles's law that says that volume and temperature are directly related. Um, then that's only at constant pressure and your temperature in kelvins. Charles's law proves the existence of absolute zero because what this is saying is that you can measure the volume versus the temperature of a gas, and you can then extrapolate out to see at what temperature the volume would reach zero. Then there's Avogadro's law that says that the volume is directly proportional to the number of moles. But when we combine those together, we get what's called the combined gas law. This is the only one you really need to know out of all of that. And it's on your reference table. It says P1V1 over T1 equals P2V2 over T2. You should have worked with this before in honors chemistry. The important things are that your pressure on each side and your volume on each side have to be in the same units. You can't use, for instance, kilopascals over here and torr over here for your pressure, or liters and milliliters. And your temperature has to be in kelvins. So that's the combined gas law. And then there's what's called the ideal gas law, which says PV equals nRT, or I like to shortcut this as PivNert, where R is 0.08206 liter atmospheres per mole Kelvin, or 8.314 joules per mole Kelvin, or 62.36 liters torr per mole Kelvin. Just so you know, this 8.314 is not one that we're going to be using anytime soon. We will use either the gas constant if our pressure is in atmospheres, or if our pressure is in torr. And torr and millimeters of mercury are the same thing. So if we measure in millimeters of mercury, we could also use the 62.36. Those values are also found on your reference tables. We also know that the volume of 1 mole of any gas at 0 degrees Celsius and 1 atmosphere, which is called standard temperature and pressure, is 22.4 liters. We'll use this value a little bit more in our next unit with stoichiometry. That being said, I want to show you a little simulation, and I will link this in Google Classroom. There's a few useful things in here. Under the tab for ideal gas, you can see that we can put some particles in here, and we can have them moving around, and we can see the pressure and the temperature. We can try heating the container up and see what happens to the molecules. You'll notice they'll start moving faster. One thing to notice, though, is that not every particle in here is moving at the exact same speed. Some are moving slower, some are moving faster. When they collide, they transfer their energy. If we were to make the container smaller, the pressure would go up. If we make the container larger, the pressure goes down. If we ice everything down, the pressure goes down. If we use particles that have a lighter mass, they move faster at the same temperature, because kinetic energy equals 1/2 mass times velocity squared. If these particles have less mass, the ones in red, then they will move faster. So this is a really helpful simulation. It treats the gases as if they are ideal. So you can go in and you can play with that. They have, there's another tab called Explore where you can just play around. Then there's one on energy where you can put the particles in here, and then we can watch and see a graph of their speeds. And you'll see this will very quickly begin to look like a Maxwell-Boltzmann distribution. As the particles are moving around, we can see their speeds. We can see what happens to that distribution as we increase the temperature. We can see it starts to shift towards the right. And as we decrease the temperature, the graph is going to kind of stack up with more particles having a slower speed. You can also look at a graph of kinetic energies on here, where it's taking the the mass times the velocity squared. We can also add in some lighter mass particles into the equation. You'll notice that the total average speed goes up. But if we look at the speeds of the uh, purple particles versus the red particles, you can see the red ones are clearly moving faster. Their distribution is skewed further out. We can do the same thing with kinetic energies. It's a really cool little simulation to go in and play with. I highly recommend that you spend some time with this and just explore. You can kind of see the Maxwell-Boltzmann distribution, but the modeling behind this is entirely based off of the ideal gas law and the mathematical principles that underlie it. So it's not like they're doing anything crazy in here. There are a couple more things that I want to show you before we finish this little unit off, or before we. All right, there's a few more things that I want to get through in today's lesson. The first is partial pressures. And so, in a mixture of ideal gases, the pressure that each gas exerts is independent of that of the other gases, because the pressure is caused by the collision with the walls of the container. And so, if you add more gases in there, that doesn't stop the gases that were already there from colliding with the walls of the container. You just add more collisions from the additional gases, but they're independent of each other. So, we have this equation that's on your reference tables. It says the pressure contributed by gas A equals the total pressure times the mole fraction of gas A, where that's the Greek letter chi, that's the mole fraction. So however many moles of gas A divided by the total number of moles of gases in the container, you multiply that by the total pressure, and that gives you the pressure of gas A. So then you can add up all the individual pressures. When we do the lab, for those of you on cohort C, you haven't done this yet, where we collect hydrogen gas over water, the partial pressure of water is also in that container in addition to the partial pressure of the hydrogen gas. And so we have to subtract out the partial pressure of the water vapor, which we kind of you can look that up on a chart. And then we also have Dalton's law. Here we go. It says the total pressure equals the pressure of gas A plus gas B plus gas C. So all those pressures are additive because essentially mole fractions add up. If you add up all the mole fractions of each of the gases, it has to equal 1. Right. So next, gases and work. This is not really going to be tested on the AP exam, but I feel like you should see this. So for those of you who take physics, you'll learn that work is exerting a force over a distance. And so whenever a gas expands and it causes a piston to move, the gas does work on that piston and transfers energy to it. And that is the principle behind an internal combustion engine. So this is a broken internal combustion engine, but it has a piston in here. You can see you're looking at the bottom of the piston that's moving up, and then it's moving back down towards you. So this piston moves up and down and turns a crankshaft. And then up at the top, it's got some valves that are controlled, and it's able to suck in an air-fuel mixture through this carburetor. And then it expels it through this exhaust pipe right here. And so what happens is this piston comes down and it sucks in air, it compresses it, then a spark plug would ignite it. Spark plug would go in this little hole right there. I would ignite it right as that piston comes all the way up in the cylinder, and then the gas would expand and get really hot and push down, and that's what actually does the work in the engine as the piston moves down. And then it would come back up and the exhaust would be expelled out, and then it would continue. So igniting the gas, generating pressure, and pushing against a piston, that's the principle behind an internal combustion engine. So I just figured that's something useful for you to know. So the last little thing we're going to hit on today is the corrected ideal gas law. So in the actual in the ideal gas law, we're assuming that gases behave like ideal gases. But as I said yesterday, ideal gases are like unicorns, they don't actually exist. So, since real gases have a actual volume, the individual particles actually take up space, and we're ignoring that part of everything. The actual volume of a gas is larger than we would predict. So, when you do the calculations of what the volume of a gas would be, and then you actually measure it, the volume turns out to be a little bit larger because you're working with a real gas. And since real gases have intermolecular attractions to each other, they kind of stick together a little bit, their pressure is less because instead of colliding with the walls of the container full force, they're going to be a little bit attracted to the other gas molecules. And so that will reduce the force that they hit the container with. So the pressure will also be a little bit less. Now, this definitely depends on which gas you're working with and the other conditions. Now, we can minimize this by working at low pressures and high temperatures. So, you will certainly be asked about this on the AP exam and on your test in this class. But gases have their most ideal behavior at low pressure, where the gas molecules are very far apart. So, we minimize the actual volume of the molecules so that most of the space is just empty space with gas molecules spread out in there. And they also behave most ideally at high temperatures because at high temperatures, the molecules are moving really fast. And so as they zoom past each other, they don't have time to set up these intermolecular attractions. So you minimize the intermolecular attractions at high temperatures, you minimize the effect of the volume of the gas particles at low pressures. Because keep in mind, if you increase the pressure of a real gas enough, if you squeeze it in tight enough, you will eventually squeeze it into a liquid or a solid. You will cause it to change state and condense. And then it's not a gas at all. That's completely not ideal. Similarly, if you cool a gas down enough, those molecules will slow down enough that they will start sticking together and forming those intermolecular attractions. And then you have condensed into a liquid or a solid. Now, gases do not behave ideally near their condensation point. So, for instance, water vapor does not behave ideally near 100 degrees Celsius or at any temperature below that. It really wants to condense into a liquid, and ideal gases would never condense. So, those are some corrections that would have to be made to the ideal gas law. There is a formula that corrects it called the van der Waals equation. We're not going to learn that in this class. That goes beyond the scope of our course, but that is an equation that could come up. So keep in mind some things that you'll be expected to do based on what we've learned today. You'll be expected to be able to plug numbers into the combined gas law and make some calculations. You'll be expected to use the ideal gas law. And you'll be expected to calculate partial pressures of a gas based off of the equations. So I suggest you look at your reference tables and you find those equations. We will do some more practice with those calculations over the next few days.